Now on to the solution of problem 2. So again, we're dragging a box along the ground at a constant angle, constant tension in the string that we're dragging it with for a certain distance, I guess in this case along a table, but horizontally. And we're going to calculate the work done by that string force on the block during the motion by Fx times delta x, and delta x, again, we've aligned our x-axis to, in this case, simplify our analysis, and it's aligned with the direction of the displacement, so horizontally. And doing that, the x component of the force, that Fx, is 50 newtons times the cosine of 20 degrees, and the x component of the displacement is just the 2.5 meters. So you put that in your calculator, 117.5 joules is how much work it does. How much work, this is B, how much work does this kinetic friction force do on the block during the motion? Well, you might be a little bit confused because it doesn't mention a kinetic friction force, but we know there has to be a kinetic friction force because we're told that the box is being dragged at constant velocity. If we were pulling a box along a frictionless table with this constant force, it would keep accelerating more and more to the right and go faster and faster. So if it's being moved with constant velocity, there must be some friction force to the left to counteract that constant x, positive x component of the force going to the right, so that there's zero acceleration. And how are we going to figure that out? Well, of course, we'll do a free body diagram, and the first thing we're going to try to figure out is how big does this friction force have to be to make the acceleration zero? So I've drawn a free body diagram with the weight, the normal force, the string force, and the friction force. Those are the forces that are on the box during the motion, and we're going to use F net x equals max. Ax is 0, so the right-hand side is 0. The string force comes in with a positive sign, and that's 50 times the cosine of 20. And the friction force, that's what we're trying to solve for here, comes in with a minus sign. They add to 0. And if we run that in our calculator, we get 46.98 newtons is the magnitude of the friction force. Okay, back to the question. How much work does the friction force do during the motion? Well, in this case, again, we're going to use that formula Fx times delta x. In this case, we want the x component of the friction force, and that's negative. The magnitude of the friction force is 46.98, but its x component, when we're using this formula, the x component of the friction force is minus 46.98 newtons, and the delta x, again, is 2.5 meters. So the work done here is negative, and it's exactly the negative of the work done by the string. Friction does a negative work, the string does a positive work. Okay, we're just trying to figure out how to calculate these things. We'll figure out why we're interested in the notion of work in the later sections. Part C, same worksheet problem. How much work does the normal force do on the block during the motion? Same formula we're going to do. Take the normal force x component and multiply by delta x. If we look in our coordinate system here, if it's displaced along the x direction, the normal force component along that x direction is 0. So this nx is 0. That means the product is 0, and the work done by the normal force on the block is 0 during this motion. Let's try to pull some of those ideas together that we saw in the previous example. So this is the free body diagram of the forces on the object as it's moving from initial to final. And in this case, we notice that the normal force and the weight force do 0 work because they have no component along the direction it's moving. The string force is more or less along the direction it's moving, so it has a positive component, and that means the string force does positive work. And the friction force is exactly opposite the direction of the displacement, so it does negative work. All right, let's do a voting question, and you're going to have to use your imagination. I'll give you a moment to think about it, and then we'll discuss the solutions, so you can just think about it in your head. Here's the same graphic I've used in other voting questions before. 3 kilogram mass on a frictionless inclined plane connected on a string to an ideal kind of pulley, and here's a 1 kilogram mass hanging down, and we're going to let it go and just freely fall, and of course it's going to accelerate. This one will accelerate down that way, this one accelerates that way. And the question is, which of the following works is negative? the work done by the tension on the 3 kilogram block, the work done by the tension on the 1 kilogram block, the work done by gravity on the 3 kilogram block, or by gravity on the 1 kilogram block, or more than one is negative. So think about that for a minute. All right, make your vote. Here's the correct answer, B. Let's go through the options here and discuss why B is the only one that's negative. The tension is pulling on the 3 kilogram block down and to the right in that direction. And the 3 kilogram block is being displaced along that direction. So the tension force is doing a positive work because the tension force is in the same direction as the 3 kilogram block is being displaced. For B, the work done by the tension on the 1 kilogram block here, the 1 kilogram block is going down, the tension is pulling up, and anytime a force is more or less opposite the direction of its displacement, or it has a negative component along the direction of its displacement, you get a negative work. So this one is the correct answer. That's a negative work. Work done by gravity on the 3 kilogram block. The gravitational force is along this direction, straight down, and the displacement is in that direction, and so the gravitational force would have a positive component along the displacement there, so C would be positive work. D, also positive work. 1 kilogram is going down and its weight force is going down, so the weight force has a positive component along the direction of the displacement of the 1 kilogram block, and therefore B is the only one that has a negative or specifies a negative work. Okay, again, just to put it all together, because it's important, we'll find when we're doing problem solving, to have in our head whether a work that we're calculating with is positive, negative, or zero. And you can know that more or less intuitively. Positive work means the force, if a force is pulling on an object, positive work means it pushes or pulls more or less in the direction of displacement or motion. Negative work means it pushes or pulls more or less opposite the direction of motion, and zero work means it pushes or pulls perpendicular to the direction of motion. Let's do a couple of examples. Imagine lifting a book with your hand underneath. So I've got my hand with a book resting on the palm, and I lift the book further away from the earth by a few feet. And in this case, my hand would do positive work because the displacement of the book is up and my hand force is up, whereas the gravitational force or the weight force of the book would do negative work on the book because the displacement is up, but the gravitational force is down. If I think about the same situation, but I lower the book down with my palm underneath, again, the force directions are the same as they were before, but now the displacement is down, so the gravitational force does positive work, and the hand force is opposite the direction of the displacement, so it does negative work. If I carry the book horizontally with my hand underneath, kind of like a waiter might carry a tray of food, then in that case, both the hand force and the gravitational force do zero work because the book is being displaced horizontally, and those forces have no component along the direction of displacement. In other words, they are perpendicular to the direction of motion in this case. And finally, if I imagine just holding the book motionless, so I have the book held in my palm and I say that's the initial state, and I just hold it there and I say that's the final state as well, then during that whole process, the hand force does zero work because there's no motion, there's no delta x or delta y in that case, and so does the gravitational force. The reason I bring this up is because normally we would say if you're holding a heavy mass in your hand, in the common way of speaking, we say that I have to do a lot of work just to hold it there. In other words, it requires effort, but the physics notion of work is different than effort. You have to be applying a force at a point that moves through space in order to have the possibility of doing work. So even though it takes effort to hold a book, my hand force is doing no work in the sense of physics. All right, let's stop and take a break there.